You're doing great. Welcome to the 16th part of HULATAM webinars, info sessions. In these sessions, we plan to introduce Harrisburg University, the available resources that we have, the research that is going on, and kind of like informal way of introducing the university to you. My name is Ruzbe Sadikian. I'm an associate professor of data analytics at Harrisburg University, and I have the honor to be the host of these sessions. Harrisburg University is a private STEM-focused university in Harrisburg, Pennsylvania, with an additional location in Philadelphia. We have more than 30 programs from undergrad, grad to PhD levels. We have around 6,000 students who represent 110 countries. And we are so happy to say that now we are moving to Panama. We're moving to South of America. We start with analytics, but we're going to offer more and more majors from project management, computer science, some cybersecurity, and so on. These classes are going to be delivered in a hybrid format, which means it's going to be both online and on campus. And it's going to be taught by instructors from Harrisburg University of Science and Technology. We're also going to offer the latest cutting-edge professional development classes and courses too. For the first few cohorts, we also offer scholarship. After the end of these sessions, we really appreciate if you take some time, it won't take more than 2 minutes of your time, to fill out a survey that would use this QR code. I'm going to reshare this page again at the end of the session. So hopefully just spend 2 minutes and respond to the questions. If you have missed our previous sessions, they are all saved and stored on YouTube channel of Harrisburg University. Again, you can scan this QR code and get access to all the previous sessions. But for tonight, I'm honored to have Dr. Majid Sha'lan, who is the professor of computer science and director of computer science at Harrisburg University of Science and Technology. He is the director of computational science PhD program, the HPC Research Lab, and Advanced Research Exploration Initiatives as well. Dr. Sha'lan earned his Bachelor of Science in Mathematics in 1987, his Master in Computer Science in 2000, and his PhD in 2006. His research interest includes simulation and modeling in artificial intelligence and neurocomputing and multi-core and GPU architecture. Dr. Sha'lan previously taught multiple courses at Colorado School of Mines, University of Colorado, Denver, and University of Denver for both grad and undergrad students. Along with Dr. Sha'lan, we're going to have some of our Avid PhD students that Dr. Sha'lan is going to introduce them. So the floor is yours, Dr. Sha'lan. Stop this. You're muted. You're muted.
They muted me. Hello, everybody again. Thank you, Ruzbe, for the introduction and for the opportunity. My name is Majid. It's like magic with a D at the end. And as Ruzbe mentioned, I am the professor of computer science, in the means that I built like undergrad, masters, and the PhD when I was alone, hired in the university 10 years ago. So, and a pleasure to maybe give you an a preview for the program. And I thought the best way to speak about something is to let like the students who are kind of the harvest and the fruit of our little experiment to talk about the technical stuff. Ruzbe and I had some couple conversations that we thought would be we're going to come back again to talk about more about stuff. So this is what we're going to do. I'm trying to do like stopwatch so I can probably hold myself to the time. So let me just go through some of the I got a presentation here for you just to make it like kind of visuals and clear to everybody. So, and I'm gonna kind of stop the camera so you can have all the focus on the slides, which is basically here. Do you guys see clear?
Yes.
My slides? Wonderful. Thank you so much. So let's check it out. So basically, the idea came from, part of our, we've been enjoyed this very, liberal, open, flexible atmosphere at HU to build what we think would work best for the students, and as a collective experience for the whole programs and for the visionaries and the leadership of the university. It seems like we have been on the right track, and most of us in the programs feel that there is something that we can share with the world that is special, and that's where this, outreach to Latin America with Dr. Huggins and Rosbe and the others is part of it. So uh, let's get to the action here and see. So in computing, we are always looking at challenges that can probably motivate something. And the challenges that are, since first day of mechanical computers into all the way to what we see now of computational gadgets and stuff is started to be very complicated, as you can see, in culture, society, technology, economy, governance, environments. There is a lot of challenging to computing societies. And for us, especially in simulation and modeling and complex visualization, things are getting even more complex. The whole thing, as we see, is coming from the need for few things. Naturally, the need for speed, which is justified all by when Moore's law in expanding the number of transistors on a square inch came into an end, and then the single CPU, although with all efforts of overclocking and stuff, reached like a dead end. So the need started to be for some high performance machines and supercomputing. And all of that, probably one of the things that I wanted to share with you, all of that were just like came from 2007. All of these things that you see here in 2007, and it's only because of the big economical hit 2008. The world didn't pay attention to that, but most of the what we see now in the computation in the world of computation is triggered by these companies and startups, and who are now the moguls in computation. You might probably see this like not very related, but you need to know that all of those guys, they were not able to get into this level unless they jumped into high performance computings and they built their own data centers and gigantic servers that you hear about in Google and other companies, that engineers and programmers are moving on scooters inside these buildings. So that's what brought all this world into the high performance computing. So we felt that this is a responsibility now, that we have to have our students up to speed with the world. And you can see this is what is on the cloud, the supernova, all of those guys. And this is probably a slide that is old, in all different types of computation, full of divers and companies. So from our perspective, what we have accumulated on us here is a huge amount of data to analyze. Everybody knows the story of big data. A numerous number of variables in every system and every problem that you handed out to you. There is a need for more people to have to be just like hands on decks, so they can solve problem, and then the security issue as well. So and for us in computing, because we are algorithms guys, we think it's the high dimensional, multi-threaded, multi-tiered hypotheses that we should examine every time. What else? There is a lot. This is from 2014, and this shows how big data started to get very cheap. So this is the cost of data per megabyte and the speed of transfer. And you can see this is going beyond what anybody have thought. And then the world or the computation guys, computer science and others started to think about, oh, what kind of storage is supposed to be able to handle that? What kind of compute can handle such problems? And that's where things started to push toward what we're talking about right now. Another change was the human adaptability to technology, which is technology can see in this curve going all the way up, and then human adaptability is not going in the same curve. And that's what triggered the need for automation by all means. And then you get the revolution of citizen science, where teachers have telescopes and contributing to the field of astronomy. And this is basically a real story where one of the stars is discovered by a middle school teacher. Some others, that was called like the Galaxy Project. Some others, math teacher solved a problem that is 100 years, standing without a solution, and so on. So people start getting empowered as they are getting access to all of these technologies and the scientific, practices. Um, see what else do we have here? So with that, all kind of complexities risen to the level that scientists started to think about how can we get into some efficient data structures, whether they are static as we know the data structures, or where they are dynamic on when you create a data structure in a very efficient way on a GPU on the fly and then erase it and then change it to optimize your solution, and then more sophisticated algorithms that are needed. And that's the point about the democratization of computing, that everybody has the right, should have some access to technology to be able to utilize it. And we have in the United States a lot of, and I'm sure everywhere else, a lot of projects getting people to get into the coding and such and such. So this is what we have thought is coming to us, and we have to stand up for this challenge. And that what motivated the vision, which is as a University of Science, Technology, Engineering, and Mathematics, we have to have some computational component or some ultimate machine. And that was my dream, actually, to build an ultimate machine that can probably cultivate the whole other parts of the projects. So in that machine, we thought it's going to be computational sciences, because we always thought computer science supposed to be, positions all other natural sciences and other like economy and engineering and stuff like that, in a way that we replaced maybe the old mathematician who is accompanied every group of researchers. We also thought that it would be the ultimate tool that we understand and we utilize always to model world problems, which is mathematical modeling, to capture systems and their dynamic. And then we also thought that it's all going to go down to some articulate simulation for some behavior of a system, and reflect on the dynamics in between the variables, and then maybe build some predictions and forecasting systems. We also thought that it would be very crucial to us to have a scientific computing method as a practice. And there is a lot into this, maybe in the coming slides, or maybe for future meetings we can talk about it. We also thought that this machine is going to help us to do all the analytical work for any problem under hand. And from our perspective in computer science, these problems are of two types: the theorem proving nature of problem solving, which is forward parametric chaining, as classical mathematicians used to go with the proofs, and also the backward non-parametric chaining, and that's the core of the weak AI, or what is so-called um, machine learning. And at the same time, we thought this machine could help us probably, optimize our techniques on different fronts, and then, make a good leap toward having our own solutions. So this is our interest as a, STEM, science, technology, engineering, mathematics. And for each one of these, we had some, thoughts that we infused in our curriculum. And what you see above here is one of the objectives in the programs that is coming from long, analysis for these things, because everything what mathematics means to us means discretization any problem that we get from the real world, then mechanize it through the ultimate, computing machine, which is basically so far it's a Turing machine, and then build models on top of that. We utilize the scientific computing, answering the 4, 5, 7 questions, no matter what you want to count them, about almost everything. And this is the curiosity that a scientist should have. And you probably recognize these steps. And this guy right here is not the first one who created, but we always use him as, marketing thing for whatever we say. From our perspective in computational scientists, scientific method is, moving or triggered by these steps between phenomena, then the modeling, then the computing, and then the simulation, which is, by these steps, we always think as the best practice to tackle any problem. And then you have the scientific findings, and that is supported by the three main pillars of scientific research: experimental theory, experimental, which is kind of physics; theory, which is basically mathematics for verification; physics for validation for any experiment; and then you have computer science and other computational sciences with the simulation techniques. And there are, cycles for feedbacks and redesign always amongst all of those. So in the engineering, we are software engineers, and we are kind of riding on the wave of automation for almost everything. And we propose ourselves as blacksmiths who build tools and sell it to other people, maybe more prominent data scientists, students, faculty, researchers. But that's our part, their part, to get feedback so we can enhance our build or make. One of the things that we came to realize that we need to inject in our curriculum and teaching is that we got to get into low-level programming on direct machines. So our students are working on writing codes in C++, on GPUs, on memory modeling, and all, manipulating the threads and other transfer registers on multi-cores and GPUs. And that makes them probably having a better opportunity to have something under their names to develop some really interesting solutions. All of this is tied up to each other because, all computational stuff that is going on is one of two things. It's either high performance computing, like server-based stuff and supercomputers, or it's an embedded system, a system on a chip on something, a drone or a washing machine or whatever. Tying all of these is the cloud computing, and we have this also present in the program, at least implemented. And basically, this is the thing that we built the high performance computing laboratory based on. So now, and collectively, our vision turned to be four things. We started at home. We got to empower our faculty and our students to be research scientists. So we did something down there, the build of the HPC, and then the reach out to the research centers, and then the PhD program is one of them. And I'm going to talk about each one of them a little bit here. So we started HU to line up all our computer science programs, at least the 3 programs, and maybe information system, information technology as well, to be on the same curriculum when it comes to research of undergraduate, master's, and the PhD. And that's, an illustration for how these things are coming together toward, building a vessel of a research for computer science. At least that's my belief and my program belief. And of course, we have done some good work here. This is probably mostly encouraged by presidential research grant at HU, which is $20,000 a year, which is we got this probably 7 times so far, maybe more. And this is some of the work of the undergraduate students. We have some students in the undergraduate published in IEEE and ACM with their faculty, of course. Then we got into the masters and we lined up people with some good, roadmap for achievements and best practice to have a master's research. And we also hooked them up with the high performance laboratory, which is based on a research unit that's represented here, where a qualified faculty can teach and research and can also have a good exposure with her students to all other stuff that can be done inside here: course developments, software DevOps, orchestration, other research stuff, experiential learning, and such and such. We are sitting now on 4 production clusters, 10 terabyte of RAMs, 2,000 cores, 1 petabyte of storage, and 12 GPUs from different generations. And this is impressive. This is a dream coming true. All of these are small donations and reach out to society and community and help of collaborators, which is a great deal. Some other university would build a high performance machine. Things start at 5 million and up. We did that with blood and sweat and efforts of people, and it actually made us better ourselves. So that was a good investment to us. What else do we have? Stopping here. Okay. So this is our outreach. We got to, reach out to like NASA, Oak Ridge National Labs, NVIDIA, public libraries, Exceed, and others with different projects and different collaborations around the 3 levels of undergrad, master's, and PhD. Then we, on top of all of that, here comes like the cherry on top of the ice cream, is the PhD program, which is very well built in a way that is really encouraging innovation and creativity, where the second milestone is not classical, everybody sits in one classroom. It's actually based on the student's research, interest, and advisor, and they can go with any advisor in the university, in the program, with direct studies to study 6 credits. And then, so we have also here, we implemented like fork and join. After the bread, they go with their advisors and they go with their own world to do their initial thoughts, and then they come back to the main flow for the program, for like the formal education of how to publish research, how to attend symposium, how to do seminars, and how to write a thesis about a research that has an impact on society or contribution to the field. We also hooked ourselves up with NSF with a kind of a partial grant with Exceed, which is a great society for top scientists in computation that facilitate access to researcher to supercomputers. And we did have this in some of the projects. We had our students to implement, say, like simple projects, calculating the area under the curve, by approximating it with like 2 million rectangles on 500,000 cores. Just like for the sake of the practice and learning, we didn't get yet into big grants on our own with this, but it was like really helpful to see what the others are doing. So the program is in the middle of, as again, central to the all sciences. We are really interested in two types of students: a natural science students who has a problem and needs help with a computational solution to solve it. And that's basically one of the big stories in computer science. I have friends who are sitting, at least one friend sitting in the board of Microsoft team as an engineer, who was basically a chemist. He had a PhD in chemistry and he needed to do parallel processing. And he was the one who created OpenMP, programming language for vector machines in the early 80s. And that's the story that we thought would be, better for our students to be in this domain to research rather than pushing against like Google, Microsoft to build an operating system or a new general programming language and such and such. So again, that's the flow, and that's the advising roadmap for the students. That is very well thought of, and all the compartment here stands for courses in the curriculum and advising stopping point, hard stopping points to perfect the final, thesis dissertation for the PhD students. We are very procedural, so there are steps that you follow at HU to get your thesis published. There are people who are, reading for you. The library is doing a great deal of help. Back to the advanced research exploration of this, this is on the master's level. We were able to reach out to 2 locations in NASA and send about 9 students to work with them in the master's. That was 2 years ago, like before the pandemic. And then public labs in Brooklyn for developing some advances for their benchmark workbench, spectral workbench software tool. And then for Oak Ridge National Labs, we didn't get into that yet because the pandemic hit, and I don't know where everybody now sits. These are the other locations in NASA and the other projects I can talk about maybe in different sessions and details of these things. But it's a great thing because now the students, beside having us as mentors, the students have somebody in NASA, like a top scientist in NASA, who are guiding them and helping them throughout their journey. The supercomputing track is there. The automation track is built on that. Here are the benefits. Students are now having exposed to the top industry hubs. Faculty are now rubbing elbows with top scientists, and university in general is now more able to revise the curriculum, the visions based on the industry needs. And of course, the industry is always watching what is the next breakthrough, who is the next genius that we can pick up, and it could be any one of our students. So far we got some good grants from presidential grant, from Department of Environmental Protection in Pennsylvania, same department in West Virginia. We have a grant that we are part of now. It's under review. It's a big grant to build the data center for the agriculture and technology stuff. We have project with the U.S. Federation of the Blind to create a portable device that can help a blind person to see around and navigate. We have a project with Johns Hopkins Applied Physics Labs. This is a very complex high mathematics algorithm that we're working on. We have some negotiation with the Army Corps, the DC, and we are putting together an application for some NSF grants. This is some stuff about the program that you probably don't need, but we can talk about anytime later. The flow again of the program, and then the working groups, units groups we're building. We are open for other people to join. And what is making our program kind of special? We have some very articulate way to advise the students. The students in our program have multiple advisors inside the program and from industry. And those are all kind of part of the thesis committee and other committees that work with the students throughout their journey with us. And it's proven to be efficient, collaborative, interactive, multiple learning paths, cost effective. I'm not sure. We're not paying people right now, but in the future, you might think about it. And again, that's the roadmap that speaks to that. We have some good structured way to follow up with the students for the milestones. We, are running some project management stuff to manage the students' research. And course sequence, you don't need. We have a good understanding to what the students are going through because we've been students at some point. So, and the part that I wanted to I mentioned at the beginning that I'm going to let the students talk about the achievements of program when it's come to research. So we have the current students who are just passed their qualifying exam like 2 days ago, are going to present to you their initial thoughts on research, starting with Caleb Druckenmiller, who was already an instructor in the program, I mean the master's program, and a PhD students, then followed by Sayed, Jaffrey. They can probably jump into and change the sequence up to the readiness, and then Yao Jun Zheng in different topics, but they are all in one research unit that I am leading. It is basically knowledge graph representation unit, deep learning unit, GPU and multi-core hardware supported solutions. And there is nothing easy about, when you raise the bar, but that's how you do it. Got to take the risk. And I'm going to let the students to pop up and share their research initiatives. And I will probably come back for any questions that you guys have. Thank you. Who's coming, Caleb? Go ahead, please. Introduce yourself. Tell us your research, which state, United States, what job you're doing, a little bit, and then get us to the pure science stuff that you have. Thank you.
Yes, thank you for the introduction, Dr. Shawn. Can everybody hear me okay?
Yes.
Yes.
Yeah. Thank you, Andrea. Thank you, Rizbe. All right, so yeah, I am Caleb Druckenmiller. I'm actually from Harrisburg in the state of Pennsylvania. I grew up about an hour away from here and did both my undergraduate and my master's degree in Harrisburg University, both in computer science. I'm currently getting my PhD here while working on a few different projects within the university. As Dr. Shawn said, I was an instructor recently, and I plan on stepping back into that role very soon. And currently I'm working on the Susquehanna River Basin Commission on a project regarding river safety within the central Pennsylvania area. But a little bit about my my research interest. I just started my stopwatch because I want to make sure I'm staying within my time frame here. So as I said before, I'm Caleb Druckenmiller, and my research interest is in the world of intelligent search of knowledge graphs comprehension. So generally, this is a two-sided part of my research. One is going to be heavily focused in neural computing, and the other focus is heavy in knowledge graphs. Now, you're probably wondering what are those two things, and I'm not going to bore you with a lot of the details because I'm sure not too many people are actually interested in that outside of my cohort and Dr. Shawn. But
Caleb, you're not sharing your screen.
I am not, no, because Dr. Shawn, you're still sharing your screen, I think. Let me see if I can take it away from you. There we go. Can everybody see my screen now?
Yes.
Yes.
All right, I'm gonna take a step back. This is just the title slide, so nothing too important there. But as I said before, Caleb Druckenmiller, that's how you spell my monolithically long last name. I am a PhD candidate here, as I said before. But yeah, so my research is in the area of neurocomputing and knowledge graphs. So neurocomputing is a branch of machine learning. It's had its roots in deep neural networks. Mostly my research is in RNNs, transformers, and GNNs. All neural networks are based on this idea of using small calculations repeated over large networks, and networks are interconnected nodes in which values are passed, making small alterations via what we call activation functions, and then weights and biases. And then it goes through issues of backpropagating, and again, a lot of math that I'm sure not too many of you are actually interested in. But that's the idea, and that's what drives a lot of the current state of technology in the world today. Are the auto completion in your email you probably use to reply to an email today is a form of machine learning using natural language processing. The ability for your phone to recommend restaurants to you is a form of machine learning. So this is kind of the realm of technology that our entire cohort is targeting, and I'm sure they'll all talk a little bit more about what their specific realms of neurocomputing are talking about. But mine is focused on two aspects, really: GNN networks and transformers, which are a natural language processing neural network technology. But graph neural networks are neural networks performed on adjacency matrices, because adjacency matrices are what are used to describe graph data structures, and graphs are exactly what they sound like. You can think of it in like a social network where you have two people would represent nodes within the graph and their connections back and forth, whether it's a friendship relationship like in Facebook, where you'd have a bidirectional connection, or say in Twitter where it's a follower and followee, where it's just a one-directional connection. Similar to that is how we represent all graphical graph data structures, and graph neural networks are the way that we can run neural network technology on graph data structures. They allow for just the complex knowledge graphs that are going to drive my research to be created and traversed in intelligent ways. And more on knowledge graphs here in a second. And then transformers, the other half of my neural computing, is a technology team by Google, specifically the Google Brain Trust that was created in the early 2000s. It is an NLP tool. It comes from the paper called "Attention is All You Need." It's actually a very interesting read if you're at all interested in how words are taken into a system and you pull the attention or what the subject of the sentence is about automatically. That's this paper, "Attention is All You Need." You should Google it. It's probably the first thing that pops up. And what transformers allow us to do is they allow us to increase the training speed of neural networks, specifically natural language understanding or natural language processing, NLU, NLP models, over, say, RNNs, which are recurrent neural networks, which were how we would have done natural language processing in neural networks about 5 or 6 years ago, prior to 2017. The idea of using attention in transformers is that we can ingest the whole corpus or the whole text into the training apparatus that we're using, the neural network we create via one of the frameworks, PyTorch, TensorFlow, etc., and apply the whole system through a GPU instead of doing incremental training, because of the way that neural networks, recurring neural networks work. If I can grab my pen real quick, was this idea of, and draw circles here. Every time we feed one piece of data in, we have to look to the one piece of data behind us to get the context of what this word data is. So that's the idea of recurring. We frequently have to see what was behind us, what was the recurring data that we're seeing. So let me resolve the ink there. So now with transformers, we can do this all at once and grab onto the attention of the corpus or of the sentence itself and do our neural networks based off of that. Knowledge graphs showcase relationships between knowledge units. Just like any graph data structure, the idea is to represent data and show their connections. The relationships indicate a route of learning for the knowledge graph. An ascending connection in my knowledge graph would be a step forward in the learning process. A descending step would be a step backwards if a user is struggling. and the supplementary connection will be supporting knowledge of units expanding information in a particular area. My idea of the knowledge graph that I'm working on is actually going to be a teaching aid. It's supposed to model the curriculum for a certain either course or an entire degree platform and showcase what are the knowledge nodes that a user is hitting. So it's a math program, you could do linear algebra, calculus, geometry, and it would show the various white papers, textbooks, and assignments being used within that curriculum, and what are the best ways to go about teaching those sections, as opposed to relying on a textbook, which may be out of order compared to what you would think, you as the teacher would think would be the best way to navigate the course. This is going to tangibilize that way of describing the best steps forward through a curriculum. Going to be the database data storage solution that I'm going to be using for the graph data structure. It's similar to SQL and NoSQL, but stores the data in a graph data structure, and also provides a visual representation of the graph in Neo4j and the Bloom interface. It's also queryable with the Cypher query language, and all of this is great, but I'm going to be creating my own domain-specific language on top of Neo4j and Cypher to show a dashboard and visual representation of what the data would look like and what are the shortest path and best paths through the knowledge graph that describes the curriculum for a user to ingest. An example, I would like to show what this Neo4j platform looks like. I'm going to pull it over. You should still be able to see this as I'm sharing my whole screen. But if you can't see my browser, please someone say something in chat. But otherwise, as you can see here, this is the idea of a graphical database. Instead of a tabular format with a table and datas, it's all nodes, and these nodes have various aspects to them. They have various information. Here is a link and a name, the properties, various relationships that they have. And this is a graph of Stack Overflow questions. So on the right side here, you see the blue dots, which are not here, are answers. The red are comments. I left those out. The important ones here are the users, the tags, and the questions. So in here, we have various questions being asked in the yellow, and then the answer, or the users that supplied those questions, and then the tags that go along with those questions. And the idea here is we want to relate the way that a person who asks a question is asking a question about a certain topic may also be asking questions about other topics. So if you're asking questions about TypeScript, you may also have questions about JavaScript, jQuery, and other JSON perhaps. And we want to see how related and how frequently are you asking these questions and what order you're asking them in. And this kind of showcases a way that progression of curiosity or progression of difficulty in a project of something like programming. An additional use case of the knowledge graph data that we're showing here will be modeling Wikidata's graph, showcasing all of the knowledge graph that holds the Wikipedia data, and that would be something similar to what we want to do on a larger scale. Stepping back into the slideshow, because I'm running out of time here.
Yes,
Neo4j, pardon?
Yes, you are.
Yes. Yeah, so Neo4j and the knowledge graph will come together to create the technology that we're looking for to store the knowledge units. Machine learning will be done through the tagging of the data, and machine learning will be done through transformers, so the various textbooks, white papers, and things like that, the transformers. And then the graph data structure will be created and connected using PyTorch geometry, which is our graph neural network framework. In the last 20 seconds, does anyone have any questions?
I do. So for Neo4j is a tool. What is your contribution then?
Yeah,
To the field
Yeah, so Neo4j will be the tool that will house the data itself. The real revelation here, as I said, will be the platform in which we can showcase all of the knowledge units within a certain curriculum and describe a best path. So the real novel contribution to the we'd say computer science will be the algorithm that is going to discern that best path. It'll be the traversal algorithm and the connection model that will be created via the transformers and the graph neural network system to connect the knowledge graph. So knowledge graphs exist, but we want to create a hyper-focused knowledge graph on the curriculums that are based within a either university or a local school district or just a class itself, we're going to be able to ingest that data and create a custom knowledge graph for them, which will be part of the algorithm, and then a secondary algorithm to traverse the knowledge graph to suggest a best path or supplementary material.
Does this include dashboards, domain-specific languages?
Yeah, as I said, there would be a domain-specific language to query that knowledge graph, to add various instances, or to add supplementary material. Would be one way to use the supplementary, would be to use the domain-specific language. And then also the dashboard will be similar to Neo4j, showcasing your curriculum, but also would show the clusters of, say you want to describe the classes that were within the larger degree coursework for an entire degree system at a university. We could show clusters of classes and the various learning outcomes that were coming from each class, and show an overlap in the learning outcomes.
Thank you so much. Please release the share, and either one, Sid or Yao Jun, go ahead. Thank you, Caleb.
Yes, thank you, Professor.
Can you see my screen?
Yes.
Okay, let me turn on my camera. Hi everyone. So this is Yao Jun. So let me start to slideshow here. So thank you, Caleb. So this is amazing presentation. So I take over here. So my research area is mostly a little bit different. So it's focused on natural language processing, pre-training. So I also focus on the specific design model about the prompt. And so a little bit about myself. Currently, I'm a PhD candidate from Harrisburg University. I registered at the same time with Caleb and Sid. Previously, I was also kind of study 2 years from Harrisburg University of Computer Science. And before that, I was a master degree of information management from Syracuse University. And back around 10 years ago, I was study like economics from Beijing Normal University, and also another bachelor degree of Russian literature. My work is right now is a senior data engineer. And in China, I also founded a kind of consulting firm about the data and the AI company, and the name is Guangwei Inspire company. So about what my research is, so it's about the specifically is a pre-training model. We call it PLM, and also specifically for the PLM model. So I narrowed down to the to the prompt model. So I'm not going to describe very details about what the pre-training model looks like, but I want to show you about why I would like to design the prompt model. It's mostly because with the volume of the pre-training model increase extraordinary, so we need to have more lightweight the model in order to have better performance. And also, the focus on research actually gradually shift from the traditionally pre-training task from supervised model. And also, we like to have more model. The previous model usually is more like pre-train, fine-tune. So that applying the pre-training language model downstream task design training object according to the downstream task in the pre-training and fine-tuning stages, and adjust to the PLM ontology. So the performance of the model depends on both the use template and the transformation of the answer. And the problem is how to search for the best combination of the two at the same time is very challenging. So on the other hand, multimodal research that involve both in the vision and text signals has become more and more attractive. So that's kind of inspiration about how I design my prompt model. So the prompt model actually came the idea several years ago. The idea is pretty simple. It's more like the automatically to give your a model and you answer some question. So this is a design of the model. This is a shape of the model. But I want to share with you about the very abstract about how the design of the prompt looks like. Usually you will have an input, we call it X, like the previous page, you have an input of X. Then from the template, you have template of the language. For example, we have already, it was an empty space movie. So you have some answer, either positive or negative. So the answer here is just two answer, but from the model, you might have more than two answer. You have the positive one, which is fantastic. Negative one is boring. So by using prompt model, you need to put the output from the model inside the Z place based upon the X input. So for prediction based upon the prompt model, you give the answer is combine two sentences together. So first, I love this movie. Then after you run in the prompt model, you get the answer is overly, it was fantastic movie. So under the prediction, fantastic give you the answer is mapping, which is positive answer. So this is a prompt model generally idea. So based on the prompt model, I actually designed my own model about the how to say about we call it like the MP5F multi-modal prompt-based fine-tuning model. So there is two advantages of this. The first one is prompt-based learning into sentiment prediction on multi-modality. And also, this is a pilot study of prompt on the fundamental sentiment analysis with multimodal input with few short scenario. So this is actually prompt tuning reformulate downstream tasks as similar close, problem, and abandon of task-specific head in both training and inference phases. So by this way, not just a prompt-based approach, not create new parameters on the basic pre-training language model, and bridge the gap between the masked language modeling, MLM, in the pre-training language model and downstream task. So this explains why the few texture sample also provide very competitive performance based on the prompt tuning. So in this research, I try to extend prompt tuning to multi-modality. So we call it multimodal prompt-based fine-tuning. So
I need to cut you short, Yao Jun. 1 minute, so Sayed can get his time. Thank you.
Okay, so
just wrap it up as much as you can.
We
might come again, like in different occasion.
Okay, so let me summarize. So we are going to use some data set in order to build the model. Yeah, so and that's all the reference I have. So yeah, okay.
Thank you so much. Appreciate it. Go ahead, Sayed. Please release the share so Sayed can use his. Great. Sayed, are you there?
Hi, good evening, guys. Yeah. Good evening, Professor. Good evening, everybody. Can you guys see me?
Not yet. Yes.
And my share. Is that visible to everybody? Sounds wonderful. All right, good evening, everybody. My name is Sayed Jaffrey, and I'm a PhD candidate being supervised by one of the greatest professors in the world, I would say, Professor Dr. Shalon. Caleb and Yao Jun, they're my colleagues, and they've summed up all of our research pretty well. They've covered the basics really well, especially Caleb with the basics of how graph neural networks work, and Andrea with how she's working on graph neural networks, but specifically for computer for NLP. I am trying to tie both ends of the spectrum and trying to create a new method to work on computer visions. And by the title of the presentations, you'd probably see It's exploring feasibility of graph semantic segmentation techniques for time series computer vision. So moving really quickly ahead with my background. As I said, I'm being supervised by Professor Dr. Majid. My undergrad is in mechanical engineering. My master's is in industrial automation. My second master's, at Harrisburg, was in computer science, and my PhD is also in computer science, specifically focusing on computer vision, but not just computer vision. It's a different interpretation of computer vision, which is based off of graph neural networks. I'm going to be going so fast because we are very short on time, so I apologize if I skip and go ahead of myself. First things first, the agenda of this short presentation. My core area of research, then, because all of us are in general working towards artificial intelligence. So I'm going to just, go over the stages and, the encapsulation of everything, how everything is sorted, the hierarchy of AI, and which part of the AI we are looking to provide our academic contributions towards, and why every level matters, what tools are we going to use, and what is our end goal, what do we actually want to get out of our research, and how do we want to see the world, say 40, 50 years, 100 years in the future. So moving ahead, my core area of research is, as I said, it's computer vision. Computer vision is a very broad term, and the way we have to look at it is that one aspect of computer vision is machine vision, which is, for example, you have a robot, you have autonomous vehicles, you have edge computing devices in, for example, Industry 4.0 that are doing that are performing machine learning at the edge, which is, as we know, that's called edge computing. So I mean, it's kind of like a a whole rabbit hole in its own way. But that is one aspect of machine vision. The other aspect is interpretation of whatever images we have, and once it gets past that first layer of defense, like the capturing of the image after the camera, or for example, you draw something or whatever is the second layer. Once you have the stored image, working on the image is where my research actually focuses. So what is my contribution towards all of this? I am going to be working on splitting up the image into a graph, and I'm going to be talking about why that's apparently a better approach, and why we believe it's a better approach that we're spending all of our resources on it. Quick thing is that with graphs, we are much better able to maintain relationships, and we need a lot less computations in order to approximately get the same results. But of course, it's a different type of results. It's not the same results that we're used to seeing. What is our final goal? Our final goal is to create an artificial sentient intelligence, or artificial general intelligence. I mean, it's kind of like a buzzword at the moment, but because we don't have a lot of the true amount of compute that we need to create that AGI, but that's kind of sort of our end goal. Now these are the levels of AI, and I'm going to be explaining where we fit into all of that. So we have deep learning. Deep learning is just one method of achieving artificial intelligence. Artificial intelligence itself is not a thing. It's just a combination of different machine learning algorithms working and helping each other out, and try to create a sense of AI. So we're going to be working on the second level, which is the machine learning, because we're going to be combining data from text and images, but not every form of text and every form of images. So if you try to do that and try to automate stuff, then you go into the realm of AI and AGI and sentient intelligence. So we're going to be focusing on this area in our PhD researches. So why the name? The name graph computer visions, because we have to split everything up into graphs. And what is the problem we're trying to solve? We're trying to solve the relationship that different parts of an image have to maintain with certain other parts of the image. So to give you a very simple example, we want to maintain the relationship between for example, a car and a road. The relationship between the tires of a car or any vehicle and the body of the vehicle. So we're gonna have to split up our image into its different smaller components and then tie everything together. But that is not the smart part. The smart part is to create an integration of natural language along with it, just so that on our command, for example, we want to see a moving car, we would just type in a moving car, and the relationships and the algorithms that we're working towards at the moment, they're going to be creating a continuous stream of images with while maintaining those relationships. So what is the ideal application? It is just to maintain relationships with respect to time. What are
Saeed, take your time and finish your talk. Just we'll record, so if anybody has to drop off, they can see the recording later. So finish your thoughts, okay? Go on and finish your slides. Don't worry. Finish your slides that you're doing.
Oh, okay.
So
Perfect.
take your time, okay?
Oh, perfect. Thank you.
Thank you, Kevin.
Thanks. Yeah, so what all of that is going to look like is it is going to be just like the two images that you're looking at right now. So we're going to be there are like a lot of I actually didn't know we had like a sort of like flexibility on time, so I kind of like cut my presentation short. But there's an aspect to all of that which is called like semantic segmentation. So what semantic segmentation does is that there's a set of data that a couple of data sets, a couple of very rich data sets that have annotations for pretty much everything that you can see in an image. So they have, of course, like those data sets are not like infinitely large. They're like 20 gigabytes, 40 gigabytes. They're like COCO data set, which is like very popular. Then there is AD20K data set, which is like, close to like 14, 15 gigabytes. It's like 25,000 images with in-depth annotations. So there are certain data sets that are, sort of like considered gold standards for computer vision applications as far as semantic segmentation is concerned. So what those data sets provide is semantically segmented parts of an image. And using that, and there are like a lot of other research papers that different researchers from Facebook AI Research Labs and Google Research Labs, they have already written on semantic segmentation and how we have to split up the image and identify different parts of the image. But at the moment, the kind of data sets that we have are only able to identify, for example, whatever you can see on the screen right now. So you can identify a person, or you can identify a horse, an animal, a piece of clouds, or like a patch of grass, or stuff like that, a generic stuff. So what our graph machine learning algorithms are going to do is that we're first going to have to, so in order to like make everything more granular, we are working on creating an even more granular data set with the semantically segmented images, and with even finer details, just so that we can even identify parts of an image. So for example, parts of a human body like legs, fingers, nose. Of course, like those kind of data sets exist in the world. It's not like we're doing it for the first time, but we're trying to integrate all of those data sets, all of whatever we've done already, into something that we can use as part of our semantically segmented graph research. So once everything is said and done, once we're gonna see that we have a sufficiently large data set, we might make it public, or we'll see how that goes. But we're going to be performing this kind of research, and this is the kind of graph interpretation that we're going to be looking at. So for example, at the bottom of the screen, what you can see is after everything is identified in an image, we have a man, for example, here, this boy, or like a child, whatever this is, it's identified as a man. So this boy has some relationship to the crosswalk it's walking over. Then there's a stop sign. So these are the only three identified components. So the way these three major components were identified was with semantic segmentation. What we want to do is make it even more granular and identify even smaller parts of the image, so that we can make predictions even better. Moving forward, I think I'm probably taking too much time. So moving forward, what are the recent advances in computer vision? So whatever I'm working on, that is generative machine learning. So image generation, generative computer vision, which means that we give computer a command, and on our command, it generates certain images. What is the state of the art, the epitome of generative models in the world at the moment? That is DAL-E2. This is a generative model. For example, if you I have an image down below, the black text is what the image represents. So the image at the moment is representing an astronaut riding a horse in a photorealistic style. Once you input this set of words in DALL-E2's basic algorithm, it's going to spit out that image, the image on the right. The problem with that image is that if we, for example, take a look at the next slide, the problem is that if you do that multiple times, you're going to get multiple images. So the first time you do it, you might get the image on the top. The next time you do it, you might get either of these images. The third time you do it, you might not even get any of these images. You'll get something else. So for the same text, it's not maintaining any relationship with anything else. And statistically speaking and logically speaking, horse does not belong in space. There's no way there's going to be a horse in space. So there's not any relationship maintenance. So the horse is not tied to the ground. The horse is not tied to the world. It's going all over the place in space, which is obviously not correct. But that shows you the power of diffusion models and what DALL-E can do and the photorealistic nature of all of this image generation. What we want to do is we want to try to maintain those relationships among different components of an image and then try to generate a continuous stream of images, just so that, for example, we want to write a script and the algorithm would spit out a movie. These are the limitations. So these are like what are super goals? Oh, like goals of my PhD research. So the basic goal of my PhD research is that we have to generate a continuous stream of images. We have to create an algorithm semantically segmented. First, we have to create step one is to create a semantically segmented data set with very fine granularity. Then we have to create a relationship between all of those components, and then we have to create synthetic data. And that synthetic data, as we all know, data is the life of any algorithm. The more data we have, the better it is going to be. And the more realistic data we have, the better our algorithms are going to be. So if we are generating realistic synthetic data, it's going to supercharge every existing AI algorithm in the world. Doesn't matter if it's decision trees back from like 1960s or DALL-E2. Every data counts. Every image pixel counts. So that's the goal of my PhD research. What tools am I going to use? For basic research, PyTorch is kind of like the de facto standard because of its, maintaining of its maintainability. The code is very clean. It's very, very, very easy execution. It's kind of like the gold standard for for academic research. So we're going to be definitely using PyTorch. For performant applications, we're definitely going to be using C++, and we might be creating our own small machine learning, for example, just like a library, just like Cafe, we might be creating something like that is like extremely performant that we can deploy at the edge computing devices. Then we're obviously going to be creating custom data dashboards because PyTorch does not play very nice with data. So what are our end goals? Like we can go the more data we have, the bigger our horizons are. We could go deeper into space exploration, and we can expand it to pretty much everything else. We could take the same framework, not only apply to computer vision, but also apply to, for example, NLP, or not just generate one set of images or like one domain of images. We could get we could expand our horizons in different image data, synthetic image data generations as well. As a side note, these are the books I recommend to everybody in the world. These are these books kind of like literally changed my life and how we have to tie academia with the industry. So it's The Rise of the Robots by Martin Ford, Superintelligence by Nick Bostrom, and The Four from Scott Galloway. That was it from my side. If you guys have any questions, I'd really appreciate that. Otherwise, thank you for your time, and I was Syed.
Thank you.
Thank you, Syed.
And thank you, Majid and team.
Sure.
Do you have any close note, Majid?
No, really. If anybody has a question, whether
Yeah.
now or later, probably.
Mm-hmm.
We're
So
open.
if anybody has any questions, feel free to type it in chat, or you can reach out to Dr. Shalan, and I'm sure he would be happy to help you with any possible question that you might have. Before we end this session, I need to have special thanks to Dr. Shalan and team. You did a great job. We really enjoyed it. That was the first thing that I wanted to go over. Second, during my initial presentation, I mentioned that we plan to start project management and cybersecurity. I should correct that and say that we already have project management and cybersecurity on Panama, and hopefully we are going to have more and more coming up to the area. Also, I really appreciate if you take some time, scan this QR code and fill up the form that is shared over there, just to tell us how we did and how we can improve our future presentations. I also need to thank Dr. Kevin Huggins. He is the rector of HULATAM. Thank you for being here and supporting this work. And also, don't forget that if you like this work, that I'm sure you did, that was a great presentation. Don't forget that in October, we will return with a presentation about cybersecurity. You're going to hear more about us and about the presentation in near future. Thank you again, everyone, for attending this session, and hope to see you again in future sessions too. Thank you all.
Thank you. Have a good night, all.
Good night.
Thank you. Good night.